Hello there. It is the Friday before the second week of AP testing, and that means that all of the AP physics tests will be coming up next week. I used to, when I taught AP physics, spend like the last day I would see the students before they started their week of tests, talking a little bit about some general concepts and giving a little pep talk about the exam. Since I'm not doing that anymore, I'm tutoring. So I thought I'd make a little video here so that if some of my tutoring students or anybody else wants to take a look at it, needs a little pep talk or needs some little tips and hints, here's your video. The AP physics tests have changed a little bit this year. They've kind of unified the way that they approach the topics of physics to make them more consistent between the different test subjects. They also made a few tweaks, which I think are a really good idea. They finally put fluids back in physics one because it's more of a mechanics kind of thing. And then they put all of waves in physics two. So that's, kind of a fair trade right there. A few years ago, they took out the electricity from physics one and put it into physics two, so that there's electricity isn't split up anymore, but waves was until just this year. And then they also split up the physics C exam into two full exams. It makes perfect sense because you need some time to evaluate students' knowledge of those two topics. And so there's a separate physics C mechanics exam, and there's a separate physics C E&M exam. There's always been separate exams, but usually they used to cram them into one testing period, a 3-hour period, and they don't do that anymore. So each test gets their own full testing period. They also kind of unified how they ask multiple choice questions. They make 4 choices on each question. Not some of them had 5 on the AP Physics C exams, for example. They also eliminated the 2 correct answer questions that they had in Physics 1 and Physics 2. And then they unified the types of FRQs you're going to see. There's basically 4 types of free response questions. You're going to see mathematical routines is one of them. Translation between different representations of the same phenomenon, experimental design and analysis, and qualitative translation. Now, all these, they say they're new question types, but all these question types we have dealt with before, and I'm sure your teachers have prepared you for that. But you should have a chance to look over some of the old free response questions, and even though the names of the questions have changed and perhaps a little bit of the style of the questions have changed, the fundamental concepts are still there. And so that would be my first recommendation. If you're looking for something to do this weekend, just pull out some AP Physics FRQs from your particular exam and have a go at them. They're all available online. I should say they release one set of those questions every year at least. So you can go online, just type in AP Physics, C, Mechanics, FRQ, or whatever it is your test you're taking, and you'll be taken to the page that has all those questions on it. As I said, they're also trying to emphasize some uniformity in language. This has been a long time coming. Again, I think it's a positive development. Um, like, for example, a long time ago, before they had Physics 1 and 2, they came out with objectives for Physics C that talked about um, conservation of energy. Conservation of energy is a very important topic in AP Physics. But the way they talked about it was a little bit different in Physics C from what they came up with in Physics 1 and Physics 2. For example, in Physics C, students were asked to identify situations when mechanical energy was conserved and not conserved. And sometimes physics teachers would just shorten that to say, well, when is energy conserved and not conserved? Well, the answer in Physics 1 and Physics 2 is energy is always conserved because that's not how they talk about conservation, meaning stays constant. In Physics 1 and Physics 2, they would say, I mean, quantities like energy are always conserved in every interaction. And that means by conserved, it is not created or destroyed. And so if it's not created or destroyed, then if it is to change, it must either be coming in from outside the system or going away outside the system, if there is nothing changing, nothing causing that quantity, perhaps it's energy or momentum, whatever it is, to go in and out of the system, then in that case, then that quantity is constant within the system, but it's always conserved because it just means it's not created or destroyed within the system. Anyway, we'll talk a little bit about conservation laws in a moment, but I just thought I'd bring that change to you. Now, they actually started talking about it in the same way in Physics C a few years ago, but this year I understand they've made a complete effort to use uniformity of language across all four AP Physics classes. In the course and exam descriptions, they mentioned one thing that they try to unify was how they describe Newton's third law, for example. Something else they talked about changing. So anyway, we got that going for us now. I'd like to give you a few general hints about the AP Physics tests, and then I'll go to some specifics of things you can be looking for if you're trying to answer specific AP Physics problems. First, remember that the AP Physics test is not a math test. It's not trying to measure your ability to do calculus, or even if you're taking the calculus base exam, or even complex algebra. There is always a physics concept that underlies every question that they're asking. And so if you find yourself in a situation where you're doing what seems like a lot of algebra to get an answer, you may want to step back and say, hey, am I approaching this incorrectly? Is there some principle, some property, some phenomenon of physics that I should be looking at instead of doing it this way? And it's important to remember that there are no really trick questions on the AP test. I've seen some that I thought could have been phrased better. And I've seen some that the College Board has admitted they had to throw out a question because there was some ambiguity in there. But generally speaking, they're not trying to trick you, which means every question should be about something that you could have had the opportunity to learn. They're not asking you, well, what is the fourth word in the caption on the picture on page 247? They're not asking that kind of question. I've had some college professors, maybe I haven't had them, but other people have told me they've had professors that ask that kind of thing on tests. But here, every question they're going to ask, you can always say to yourself, what concept is this question or this part of an FRQ question trying to evaluate my understanding of? And that's how you got to get good at identifying the concepts that are underlying the question, especially on FRQ questions. Partial credit counts for a lot. So if you can just get the concept down, even if you don't quite carry out the entire problem solving correctly, you can at least get the concept, and that should give you some points. And often, once you get the concept, even on a multiple choice question, that allows you to at least eliminate one or two answers, and that improves your odds greatly. So let's talk about some specific concepts that are going to appear on AP tests. And I got a little PowerPoint here with some concepts that I thought would be important. So I think I'll just share that with you all. An important skill on all of the AP physics tests now is graphing. It always has been important, but it's particularly more so since the invention of Physics 1 and Physics 2, and now with the redesign. You need to understand how to interpret a graph. What does each characteristic of that graph represent? For example, in a simple kinematics graph of, say, position versus time, well, the slope of that graph gives you the velocity then. And if you have a straight line graph, then you should be able to come up with an equation that matches that straight line graph. And the equation will be able to form, instead of saying y equals mx plus b, we're going to say x, that's our vertical variable, equals vt plus x naught, which is our beginning position here. Similarly, if you have a graph of velocity versus time, and you need to know that the slope of that graph represents the acceleration, and then the area underneath that graph represents the displacement of your system, and you should be able to get an equation out of that graph as well, very similar to what you just did with the position graph when it was a straight line. And even if your graph is not a straight line, you need to understand the idea, the concept of the slope of the tangent line. What would the slope of if you took a ruler and put it next to your graph at some point, let's say right here perhaps, what would the slope of that line be? That's what you're trying to ask. The slope of that line is the instantaneous velocity at that point. If the velocity is changing, that's how you get it. And as I said, like the area under the graph of a velocity versus time graph should give you the displacement. We have equations of motion for constant acceleration, and as was stated in the course and exam descriptions, they are now trying to emphasize the relationship between straight line motion and rotational motion. So there's some connections there. One of them is that if you have constant acceleration and motion, we can use equations of the same form to describe that motion, whether that constant acceleration is linear acceleration, like here, straight line motion, or whether it is motion with a constant acceleration, rotational motion with a constant acceleration. The equations are similar because they mean similar things. The acceleration means the rate of change of the velocity, and the velocity's rate of change of position and so forth. And so you come up with the same equation. Now, you don't translate these equations to each other directly because we're talking about different things, talking about rotation versus straight line motion. But you need to understand how you can use an analogy with straight line motion to talk about things in rotational motion. That goes all the way down the line in rotational motion. You understand how Newton's second law in straight line motion is the same idea as expressed in rotational motion with Newton's second law for rotation and so forth. Anyway, these equations then for rotation are kind of gimmies because you already know them for straight line motion. You need to understand about projectiles. There's often at least one question about projectiles on every Physics 1 or Physics C mechanics exam. And the basic idea there is it's just two kinds of motions in one. If you have an object, let's say, that rolls off a table and flies through the air, once it's in the air, it's under the influence of just gravity, so it becomes a projectile. And the basic idea is that the horizontal motion is given by your constant velocity formula. So you could just say, the x position at any given time, the change in the x position is going to equal the velocity in the x direction times the time. And then the y direction, well, that's constant acceleration. That's just like free fall. So you'd use all those equations of constant acceleration and motion using the acceleration equal to a negative g. And that's another one too. Anytime you have something in free fall, in only under the influence of gravity, the acceleration is a negative g. So if you throw something up in the air, it rises up to the air. At the highest point, when its velocity is instantaneously at some point zero, the acceleration is not zero, because if the velocity is zero in the y direction, and the acceleration is also zero, so it's going to stay there. If the acceleration is a negative g, though, which means that even though the velocity is zero, the object is going to keep falling because it's going to start getting a negative velocity now. So that is pretty much the main things you have to know about kinematics. So if you have a problem that involves kinematics, try to look for those things there. Many problems deal with equilibrium. An equilibrium problem is one which they say, or you can understand, that they say something is moving with a constant velocity, or it is at rest. It stays at rest. It doesn't move. It doesn't rotate, something like that. In that case, then you have a problem to dealing with equilibrium. And to answer that, you need to use, well, you can call it Newton's first law. You can say an object at rest or in straight line motion in a constant direction does not have a net force acting on it. And so the key there is to draw a free body diagram, because that's the free body diagram is what's going to allow you to determine, what the forces are. If this thing here represents a ball that's being held in place by two strings, we take the ball as our object, and then we can draw the forces acting on our ball, including the force of gravity, which acts straight down. Usually we express that as m times g. And in a free response problem, they'll often prompt you to fill out a free body diagram. That's that's not a just busy work. It's important that they try to lead you through the answer in a free response problem on an AP Physics test. So if you draw a free body diagram like this and you call this force of tension 1 and call this force of tension 2, and then you have them all labeled, after you do that, then you can use either equilibrium ideas, in which case the sum of the forces in any given direction, or the sum of the force in the x direction had better add up to 0 because it's an equilibrium, and the sum of the forces in the y direction should add up to 0. You can also have a similar situation occurring when you have something that is in equilibrium, so that is not rotating. It is either at rest rotationally or it's rotating at a constant speed. Like in this case, I was trying to draw a little ladder leaning against the wall. In the case of a extended object like that, and we're concerned about its rotation, we have to draw an extended free body diagram, in which case we just draw something that represents the object itself, like perhaps we're going to draw a straight line, and then we're going to draw the forces that act on our object, also drawing where they act on it. And so over here we have some force, and if they say there's no friction there, we know it's just normal force, but there could be friction. Very often what we'll do is we'll say, okay, we're going to use this point up here as our axis of rotation. Is not really an axis of rotation because this thing isn't supposed to rotate at all. But we can pick any point on our object and call that the axis of rotation, and then we just figure out all the torques relative to it. And of course, down here we could have a normal force going up this way. And we also should have, because the thing would tend to slide to the left if we did not have also a force of static friction going this way and so forth. So for static friction. And once we draw all the forces that act on our object, we can say, okay, what are those torques that are produced by those forces? And then we should say the sum of the torques adds up to 0. So it's the same idea as we just did a moment ago. All the torques that act on our object should add up to 0. So that's a concept of equilibrium, and it comes up a lot in AP tests. So what if it's not an equilibrium? Well, very often then the next question I'm going to ask is, what is the acceleration of something? Or maybe you have to find the acceleration in order to find out something about it. Maybe you need to know the acceleration so you can determine, using your kinematic equations, what the graph is going to look like, or how far the thing's going to travel in 2 seconds, or whatever have you. In that case, anytime a question on the AP Physics exam asks you about acceleration, think to yourself, this is probably about Newton's second law. It isn't always the case, but sometimes they just want the definition of acceleration. But very often, that's what we're doing here. We're using Newton's second law to find the acceleration of something. So take an example like a system like this. You have a little disk, and that disk is mounted horizontally on an axis so that it can rotate about that horizontal axis. And there is a rope that is wrapped around that disk, and that rope extends down to a mast down here. And that object has some mass, as I said, and it's going to pull down. So then we have to say, well, what is the acceleration here? Well, we got 2 objects moving, so we can make 2 equations. We can say, hey, the one that is hanging down, that hanging mass, it has a net force acting on it, and that net force must equal the mass of the thing times its acceleration. The net force that acts on it would be the force of gravity, which, just for today, I'm going to make the force of gravity being positive. So I would say mg, that's the force of gravity, minus the tension force in the string is going to equal ma. And then we come up to the other object. This object is a rotational object. It can rotate about an axis. And so we can say, well, the torque of this thing the net torque must equal to I times the angular acceleration. The only torque I see acting on this thing would be the torque caused by that net force. And so I'm going to say that net force, sorry, by the force of tension, that tension force times the radius of my little disc here is going to be my torque. And so that torque should equal I times alpha. Now we have two things we don't know. We don't know A, the acceleration, and we don't know the force of tension. Actually, I have three things we don't know because we don't know A, we don't know the force of tension, and we don't know alpha. Fortunately, if this thing unrolls without slipping, we know that the tangential speed of the outside of my little disc must equal the speed of the little hanging weight that's pointing down. So therefore, we know that the acceleration of my hanging weight must equal the tangential acceleration of my disk, but the tangential acceleration of my disk is just equal to r times the angular acceleration. So we can use those two equations along with this non-slip condition here to say what the combine all three equations together, we can eventually solve for the acceleration. That's what we want to know. So bottom line, you see Newton's second law, or sorry, you see acceleration. Think about Newton's second law as possibly your answer. Another acceleration that comes up a lot is the acceleration of something moving in a circle. If something is moving in a circle, let me just get a blank screen here for us. If we have something that is moving in a circle with a constant speed, then we know the acceleration of that thing. If something's moving in a circle, even if it's not moving at a constant speed, we know the acceleration towards the center, the acceleration that accounts for its change in direction, is equal to this. We call that the centripetal acceleration, which is equal to the speed of the object squared divided by its radius. So we can use that idea to relate, for example, you can use that and set that equal to the force of gravity, the mass times that acceleration, set that equal to the force of gravity, and that would give us, for example, a way to calculate how fast something is moving when it's in a radius of when it's in an orbit of a certain radius. So as soon as you see something moving in a circle, especially if it's moving in a circle at a constant speed, what they say circular motion, even they can say, a roller coaster has a circular loop in it, or at the top of the roller coaster, the path is circular. If they say anything about circular motion, we know the acceleration, at least we know one acceleration that's going to have the acceleration towards the center is going to equal v squared divided by r. That's required for it to be going in a circular path. All right. But another common way that we solve many AP physics problems is using some kind of conservation. As I mentioned before, this idea of conservation, the way they express it in the AP physics courses is they say that conservation is a property of the laws of nature. In fact, a mathematician by the name of Emmy Noether figured out, I think over 100 years ago now, that anytime you have a situation in which the equations describing some situation have some symmetry to them, that means there's some kind of conservation law involved there. So they've discovered several conservation laws. For example, whenever you have something that starts in one configuration and then at some time later is in a different configuration, very often the conservation of energy is how you're going to solve that particular thing. Especially if something starts up high and ends down low, or something starts down low and ends up high, we are going to use a conservation of energy type idea to solve that particular thing. Now, how are you going to use conservation of energy? Well, to use our conservation laws, as we said, conservation just means the quantity is neither created or destroyed, but it could come from the outside and into our system, or it could go away from our system into the outside environment. So we also have to know what is it that can change how much of this quantity is in our system. For energy, the thing that changes energy, at least as far as physics 1 is concerned, is work. Work is a transfer of energy. So if work is being done by external forces on the system, that means the energy of the system is being changed. So we need to learn to identify, are there forces from the outside acting on our system? And we need to decide how we're going to identify our system. Usually, if we have gravity involved, that gravity is going to be part of the system, so we can use the idea of um, potential energy. So outside forces would be things perhaps like friction that might be taking energy away from our system. Um, so we look and we see, is there any external force acting on our object as it moves through the system? And especially if it starts up high and ends down low, or starts down low and ends up high, we're going to think about conservation of energy as the way to solve it. Like, let's say we had a box sitting at the top of a hill, like this little graph is supposed to show. There is a force. If we think our system is the box and the Earth's gravity as our system, then the gravity is not an outside force, it's a force in terms of our system, but there is a normal force acting here. The normal force would act up on my little box, but that force does not do work on our box as it slides down the ramp because in order to do work, there must be a force, there must be a displacement, and the force has to go in the direction of the displacement in order for work to be done. That's not the case here because the normal force is acting perpendicular to the motion here on this ramp. Now, if there's friction and we want to treat friction as an external force, then we have to say, well, the energy of my system is not going to stay constant. Energy is still conserved, but because energy is not going to be destroyed, if it is taken out of the system by the work done by friction out of it, then we can say, well, there's some of the energy in the system is going to be lost. Sometimes we can treat friction as part of the system, in which case we'll say what friction does then is it transfers energy from mechanical energy, which is a sum of kinetic plus potential, and turns it into some other kind of energy, like thermal energy within the system. Another situation, which one is going to use conservation of energy, is if there's a spring involved. The springs, if they obey Hooke's law, they are conservative forces. The spring force is a conservative force, in which case, if you have the spring getting compressed and an uncompressed, the mechanical energy of the system shouldn't change as long as the spring is a ideal spring obeying Hooke's law. So in a situation like that, we would still use conservation of energy because something started up high or ended down low, or ended up with a spring compressed and then it uncompressed, or was uncompressed and then became compressed. And what about if something is rolling? Well, we can still use the conservation of energy. We can say, if the only force acting on this thing, if it's rolling down a hill and it's rolling without slipping, there has to be some friction, it turns out. But that force of friction does not do work on our system. So we can say the total energy of our system is a constant because the force of friction on something that is rolling without slipping, if it's not slipping, it's not rubbing against the system over which it's turning. So there is friction there, but it's static friction. And as we said, in order for there to be work done, there must be a displacement. Since there is no displacement when static friction is involved, the object is not moving against the surface on which it's rolling. The point of contact is not moving. Since the point of contact is not moving between the object and the surface, then there is no work being done, even though there is a force. So in that case, then the total energy is going to stay the same, but we also have to recognize that since this thing is rotating now, uh, let's say it starts up high, but ends down low. When it ends down low, when it's down at the bottom here, when it's rolling around, it's going to have two kinds of kinetic energy. So we'll need to relate those two together. We need to have the kind of kinetic energy that talks about rotation, which is the rotational kinetic energy. Again, using our idea that we can kind of get the formulas by thinking about what is the analogy between rotational motion and linear motion. So the rotational analog of our kinetic energy formula would be rotational kinetic energy equals 1/2 I omega squared, where I is the rotational inertia. It's a thing that in rotational motion kind of acts like mass. And omega is the rotational velocity. Now, if it is rolling without slipping, that means that the tangential velocity of the thing, that is to say, the velocity that the outside edge of our rolling object is moving, is equal to the center mass velocity of the rolling object. So we can say the tangential velocity equals the velocity of the center mass, which we just call v. But the tangential velocity is equal to r times omega, where omega is the angular velocity. So using that, once we get a formula that relates the energy up here, which would be potential energy if it starts at rest, and the energy down here, which would be the rotational kinetic energy, plus the translational kinetic energy. Once we get that, we can usually derive a formula that only involves v, because we can relate v to omega using this formula here. So again, starts at pi, ends down low, starts down low, ends at pi, and any combination between. And there can be starting kinetic energy as well as ending kinetic energy, and there can be ending potential energy as well as starting potential energy. But if it involves a change in position and height, very often the way we're going to do it is using conservation of energy. That even goes in this now physics 1 concept of fluids moving. Bernoulli's equations can be understood as applying the conservation of energy to a fluid flow. So you say, well, we have an object here. This is a tank, and this tank is full of water, let us say. And there's a hole at the bottom of the tank, or somewhere halfway down the tank, or 2/3 way down the tank, apparently. And out that hole is coming some of the water. And the tank is so big that the fluid is not really moving fast when you're at the top of the tank, but is moving faster when it comes out the small hole. We can use Bernoulli's equation, but now we have to be careful because Bernoulli's equation also includes a term that accounts for a force doing work on our fluid. And that is the difference in pressure from one point to the other. That's a net force. It ends up being a net force per area. So the difference in pressure can cause energy to be added to our system or taken away from our system as the fluid flows through our system. What we'd do is we'd say, okay, the pressure at one point in our system plus a term that accounts for the kinetic energy per unit volume of our system, plus a term that accounts for the potential energy per unit volume of our system, is going to be equal to the pressure at another point, plus the kinetic energy term, plus the potential energy term there. And if we do it right, like if this tank is up on the top, then the pressure up here is just the atmospheric pressure. We call that P naught. And the pressure right here, well, this water's coming out and back into the atmosphere again, so the pressure here is P naught. So we say, oh, well, then P1 is P naught and P2 is P naught. So it's almost as if there's no change in pressure, which means we have, again, like an isolated system. There's no external force doing work on our system, if you will. And so the energy per unit volume at one point should equal the energy per unit volume at a different point. And so then we would just use that concept to figure out what the, let's say, what the speed of the fluid must be at point 2 when it comes out of the little tube, if we know the speed at 0.1, which we're going to say is essentially zero since it's in the top of that huge vat. So it's not moving down very fast at all. So that's an example of using conservation of energy in fluids. Again, starts at pi, like at the top of the fluid, ends down low, at a lower point, conservation of energy. Even in that physics 2 and physics C concept of electric fields, we're talking about the conservation of energy here. Electric fields allow us to define an electric potential energy. And electric potential energy, we can actually define a potential. Electric potential, we should abbreviate with the symbol V, is just the potential energy of electricity per unit charge. So if we have something that has a potential over here of V1, then over here it has a potential of V2. Well, just like if we drop something in a height and it falls down through gravity, if the potential energy at this point is so much and the potential energy here is so much, so it decreased, we know that that energy must have gone somewhere else because energy is neither created nor destroyed. And the same thing here. If this thing started at some higher potential, V1, and it ended at some lower potential, V2, potential means potential energy per charge. So this charge must have lost potential energy in going from V1 to V2, therefore must have gained some other kind of energy, or the other kind of energy must be accounted for somehow. Probably going to be in a situation like this, it's going to be a gain in kinetic energy. So that's where our particle could be moving faster when it goes from a higher potential to a lower potential. Once again, looking for situation, starts up high, even in potential, and ends low, you are talking, or starts low and ends high, you are talking about using conservation of energy. And of course, in circuits, you use the idea of Kirchhoff's loop rule, which expresses the conservation of energy in a circuit. All right, but that's only just one conservation law. There's others. There's a conservation momentum. Now, momentum conservation is helpful when we don't know the details of the forces that are involved, but there are two things interacting, or more than two things could be. But we can say that although there may be external forces, they're either no net force, or we can say the force in a given direction is zero. The net force in that direction is zero, so it does not add momentum in that direction, because momentum has the advantage of having a direction. So even if the forces don't add up to zero, or there is a net force in one direction, say the vertical direction, if there's no net force in the horizontal direction, then we can say momentum is constant in a horizontal direction. Again, momentum is always conserved. That means it's not created or destroyed. So if there are no outside forces adding momentum in a given direction, then the momentum in that direction stays constant. So in a problem like this, we have somebody they're holding onto a rope and they're going to jump off this tall building and then go down to a lower building, and they're going to grab some kind of a medicine ball or something there when they get down to the lower level, let go of the rope, and at the exact same time as they're going horizontally, and they're going to grab them onto this medicine ball. Well, for the fall, start up high, end down low, we're going to use conservation of energy. But once we know how fast this person is moving when they get to the height of the ball and they let go, then they're moving horizontally and they're going to collide. And anytime you have a collision, you don't have to know all the details of the forces involved in that collision to say, hey, momentum is constant because there's no outside force in that direction. So the momentum in that direction is going to be constant. So that's how we're going to solve for the velocity once the two come together. We really couldn't use energy considerations. Energy is always conserved, but some of the energy is going to get converted into other kinds of energy when the collision happens. So we are going to have to use momentum, because then we can say, hey, there's no horizontal net force on this system, so therefore the momentum in the horizontal direction is going to stay constant. Yet another conservation law. We have this angular momentum idea. Now, the angular momentum, the thing that changes rotational motion or angular motion, is a torque. So for angular momentum, we're going to say there's no net torque acting on my system, or if there's a net torque, there's no net torque acting on the system, is usually what we say. Um, a classic example of that, before we get into this one, is, say, a planet going around the sun. If you have a sun over here, and you have a planet over here, and it's going around the sun, it doesn't have to be in a circular orbit. In fact, they're not circular, they're elliptical. There is a force. That's the force of gravity between the planet and the sun. And there is some kind of, if we use the sun as our center of our system, our axis of rotation, if you will, is centered on the sun, then R in the formula for torque is equal to R cross F. Well, there's an R, there's a radius from where the force is coming from, where the axis of rotation, if you will, of the sun to where the planet is. And there's an F, force of gravity pulling back. But R is going one way and F is going the exact opposite way, 180 degrees. And the sine of 180 degrees is 0. So there's no net torque. A torque requires a force that's kind of perpendicular to the radius vector, if you will. So no torque. That means that the angular momentum of my system is going to remain constant. So the change in angular momentum is going to be 0. Same kind of thing happens here in this situation. Here we see a skater, and the skater is turning around on her skate. Now, there are some forces that are acting, obviously, and there could even be some acting that would be exerting a net torque on the skater, but probably small enough, especially because the forces are acting really close to the center of rotation, to the axis of rotation. And so, although there may be a force, maybe a significant force, that force is so close to the axis of rotation that it does not exert much of a torque. In which case, we will say the angular momentum of this system, if you'll pardon the expression, is constant. It's always conserved, but because there's no outside torque acting on our system, conserved therefore means it stays constant. But here, the thing that acts like mass or rotational motion, the rotational inertia, that does not change. That does not stay the same, that changes. As she brings her arms in, the rotational inertia of her body decreases. And since rotational inertia is decreasing, but the angular momentum is staying constant, well, the product of those two should be the angular momentum. I times omega should be the angular momentum. So if I is getting smaller, but L is staying the same, then omega needs to get bigger. And that's exactly what happens here. As she brings her arms in, she starts spinning around faster. So just yet another example of conservation. And the important thing of conservation laws is, okay, have I met the conditions for whatever it is I'm thinking is conserved to be conserved in this situation here? Here we have, because the torque is so small, because the force is really close to the axis of rotation. In the previous one, the force and the radius were going in the same direction or opposite directions. In other situations, there have been no external forces, or the forces did no work because they did not have a displacement, or they did not act in the direction of the displacement. So that's really our conservation laws are a big one. That's going to answer a lot of questions in your tests. Another one, which we're getting a full treatment of in Physics 1 this year, we get the fullest treatment of the idea of oscillations in Physics C, but Physics 1 is going to get to use some of the equations before. Up to now, they've been doing mostly a qualitative look at oscillations in Physics 1. This year, we're going to actually look a little bit at the equations. For oscillations, very often what we're concerned about for an oscillation is a particular kind of oscillation called its simple harmonic motion. And in simple harmonic motion, you get that whenever the displacement of your system is proportional to whatever force is going to bring your system back. If you want oscillations, you got to have a force that's called a restoring force that's going to bring your system back. So if you're going to pull something to the right, you need a force going to the left. If you're going to pull something to the left, you need a force going to the right, and so forth. If that restoring force is proportional to how far you displace your system from its equilibrium position, then you're going to get a particular kind of oscillation called simple harmonic oscillation. And the hallmark of simple harmonic oscillation is that the graph looks like a sine wave or a sine or cosine wave. Usually, we imagine that often that our systems are displaced and then left at rest, and then we let go, and our system then obeys this restoring force. If the initial velocity of our system is zero, but the initial position is at some maximum, then we're going to describe it as a cosine. That's like this graph right here. We have a spring and mass system, and the spring has been, say, pulled all the way to the right at some position and then let go. So the velocity is zero initially, but the position is at some maximum. And if that's the case, then the equation of motion for that system is going to be the position is going to be some maximum amount of displacement from equilibrium, which is, abbreviated with an A because it stands for the amplitude of the oscillation, times the cosine of, and this is the way I like to write it, 2 pi over the period. Uppercase T is the period. It is how long it takes to undergo one complete oscillation. So all the way from out here to the right, to the middle, to the left, back to the middle, and back to the right. That's one period. And you can see how this formula would work, right? If you're remember using radians for our cosine here, if you put in a time little t that matches one period, so you're going to get 2 pi over the period times the period, so the period cancels out, and that means that at the time of one period, you're going to be calculating the cosine of 2 pi. And the cosine of 2 pi means it goes all the way back to the beginning. 2 pi is one complete oscillation, right? Now, we do have a phase angle in it. That's what this little angle here is called, this little phi thing. That is what we need to use if we are not starting at our maximum, letting it start from rest. If we start in the middle and give it some initial velocity, then phi is going to be pi over 2 radians. We're going to be basically 90 degrees ahead, right? But the shape of the graph is going to be some kind of a sine or a cosine. Now, in physics C, we've always dealt with this formula, but in physics C, you have to learn to recognize the situations where that is true. As I said, simple harmonic motion requires the restoring force to be proportional to the displacement. And a good example of that is what we're illustrating here is a spring and mass system. So using Newton's second law, well, in physics C, we know that we can describe the acceleration as a second derivative of position. So we'll just write F equals m times the second derivative of position. But the force of a spring on the mass, if you pull the spring a distance x to the right, the force on it's going to be a negative, meaning back to the left, k, spring constant, times the distance you've pulled it to the right, which is x. And so the restoring force is a minus kx. So using that idea here, we have a minus kx is equal to m, which is a constant, times the second derivative of x. And if we solve this, traditionally for a differential equation like this, that's what this is called, we solve it so that the highest derivative of our system is off by itself, and then everything else on the other side of the equation. Look what we have here. We have a negative, means it's the restoring force, times something that's constant, times the displacement is equal to the second derivative of the position. Whenever you have that, whenever you have the second derivative of something, the charge on your capacitor, the displacement of a spring and mass system, the distance you've pulled your pendulum from equilibrium, the angle that you've taken your little hanging rigid object, which we call a physical pendulum, and you've displaced that from its equilibrium position. Whenever the second derivative of that equals a negative constant times the function itself, the solution to that is this equation here. Very often what we'll do is we'll point out that this constant, k over m, for example, in the case of a spring and mass system, we'll write the equation. We'll say the equation is actually equal to then x is equal to a cosine of omega t plus phi, where omega then is just equal to 2 pi over t, right? And by the way, in your formula chart, it doesn't give you 2 pi over the period. It actually says 2 pi times the frequency. The frequency is its reciprocal of the period, so this becomes 2 pi times the frequency. So the formula can be written as a cosine of 2 pi times the frequency plus times t plus phi. But the advantage of writing it in terms of omega, so this is the way it's written on the physics 1 formula chart, and the physics C, we often write it in terms of omega because we can learn to look at our equation, our differential equation, and we know that whatever the constant is here, that's a negative times the constant times the function equals the second derivative of the function. We know that omega squared is equal to that function. And this happens over and over and over again in physics C. You're going to get the physical pendulum. You're going to get the regular pendulum. You're going to get the oscillations in a inductor capacitor circuit and an LC circuit. You're going to get a term that involves something that involves the force acting on the system, and then something that involves the inertia of the system in responding to that force. But you're going to get a formula of the form, a negative times a bunch of things that are constant times the function. It equals a second derivative of the function. This is a solution of that thing. And omega then is whatever that constant was that you had to multiply your function by to get it to be equal to proportional to the second derivative. That is what omega is. I'm going on about omega because then it tells us with the period, then 2 pi over f just depends on the system. It doesn't depend on how far we displace our system. It doesn't depend on what the initial position of the system is or what the initial velocity of the system is. It only depends on the things that describe the restoring force on our system. The way we usually look at it, we say the period then is equal to 2 pi times the square root of something that describes the inertia of your system. So like in the case of a spring and mass system, the inertia is the mass. It is what is preventing my system from immediately returning to equilibrium. That goes in the numerator in our formula for the period. And then in the denominator of our formula for the period will go something that describes how the force acting on my system behaves. If it's a big force for a small displacement, then you're going to get a big thing in the denominator of your formula. So for a spring and mass system, then, this is the formula that's on your formula chart for both physics 1 and C. For a regular ordinary pendulum, the thing that determines the inertial term is kind of like the length of your rope. A really long pendulum is going to take longer to go back to equilibrium, all else being equal. But the thing that describes how much force there is causing your system to go back towards equilibrium, well, that is determined by how strong the gravity is at a particular location. So if gravity is weak, G is small, then it's going to take a longer time to get back. So we have a term that describes the inertia, that's the length of the pendulum, and a term that describes how the force is related to to the displacement, which is the G for a pendulum. And you'll learn to see this formula over and over again in physics C. If you look at different types of oscillation, you're going to see you have something that describes how the system resists changes to its state, and something that describes how strongly the system is being forced back towards equilibrium. So those are some of the main ideas. I just wanted to show you that some of the things that we think of as being different ideas, they can be drawn together. Fluids, conservation of energy is very similar to the conservation of energy of rigid objects. It's very similar to the conservation of energy of point objects, rolling down sliding down a ramp or something like that. And oscillations, many different systems can be described with that same idea, where the restoring force is proportional to how far you displace the thing from equilibrium. I'm wishing the best of luck on your physics tests this week. I know you will all do well. All my students will, and I'm certainly, if you are this far and you've actually tried to do some studying by looking at some person's video on the internet, then you're probably going to do well as well. Don't get overly concerned about it. It is not the defining factor of your future. This is just one thing. It's another chance for you to shine. You will do well, but relax. And I mean this sincerely, have a good time with it. It is interesting giving a bunch of puzzles to solve. I love doing these AP test questions when they come out in the summer. So good luck to you.